All right, welcome back to EE 301. This is lesson 14A. And what we mean by 14A is I'm going to be talking about phasors and complex numbers. We'll save impedance for 14B in the next video. So phasors and complex number. Here's all the lesson objectives, but the main point of phasors, and you can read this paragraph on the official course notes if you'd like to, but the main point is that we're going to transform something that we have. So if I look at my equation sheet right here, this block is phasor. This one, phasor. This is the phasor domain, like we like to say it. This one is the time domain. And what it lets us do is the phasor domain or the time domain. The time domain is how we see our sinusoidal equations. That's why this has cosine here, goes up and down. Remember that cosine is just shifted from sine by 90 degrees. You can look in the book or in the online notes to discuss the shift. But either way, it's a sinusoidal wave. Whereas when we shift from the time domain to the phasor domain, well, this phasor allows us to more easily solve our problems. So here we see x peak goes to x. This is really an RMS phasor because it says RMS. Whereas you could do a phasor without dividing it by √2, but if we're doing the RMS phasor, then we divide the peak by √2, and then this angle, that theta, goes right there with it. So, and we said there is no x, it's v or I, right? V or I. That's what we're dealing with in that part. I'll zoom in. This is on the AC side of the equation sheet, right? And so it's v or I. We can take that v peak, turn it into v RMS, and we take the theta of v and put it into the phasor value. Now we're wondering, what is this phasor value? That angle? Well, that's the complex number that we're putting in. So the definition of a phasor is, let's erase that, need it right. A complex number used to represent the amplitude, which is that peak, amplitude and phase, which is that angle, of a sinusoidal voltage or current. Right? So we saw that we can take from our sinusoidal equation and represent the amplitude and the phase as a complex number. So if we think complex number, oh man, what is that? To me, I think vector. Where I went to college at Texas A&M, all of our calculus was vector calculus. And so hopefully we don't have to do too much calculus with our vector. Let's just stick to some of the basic vector math that we need. Now, what is a complex number? If we just remember an XY axis, we've been doing these since middle school, I think. But on the x-axis, instead of x, we're going to call this real. And on the y-axis, instead of calling it y, we're going to treat it as j. J also means imaginary. There's the value of j, which we will never plug in to any formula in this class. But it's a representation of j. And so if I was looking at the geometric representation of this, then we have two different forms, and they are rectangular, which is right here, which is plotting it essentially just the x and y axis, the real and the imaginary, right? So the real axis, if it says 6, then it goes to 6, and then the j goes to 8. So if I think about vectors, there's a vector as an arrow pointing right there to that dot. That's the rectangular form of the complex number, right? So if I wanted to sketch these, here's an xy axis, which we're going to call real. I'll put it as an R and a J. So if I wanted to sketch these, 0 on the real plus 2J. There's 2. I can just put a dot right there. I'll put it in green to make it easier to see. There it is upon that X and Y real and J axis. j, real. -5. 1, 2, 3, 4, 5. So I'm going to be along this line. -2j, 1, 2. Follow these out. There's my dot right there. And if I wanted to plot it as an arrow or as a vector, there it goes. -5, -2. Now note on your calculator, it does call it I, the complex number that we're using here. And I should highlight it. The letter J is used in electrical engineering to represent that imaginary component, imaginary I, because I is already current. We don't want to confuse you. You're already confused enough. So let's call J is I. All right, the other way that we could write this is that we could use the polar form. Polar form right here. Right, and so it's the same arrow that we were doing if I had a X and Y axis, the real and imaginary, right? That same arrow can be represented as a length or a magnitude and an angle relative to the real axis. So relative to the real axis, going counterclockwise, we can find where the arrow ends or where it's crossing. So here is 10, that's a magnitude. And often in this class, we'll see it as an absolute value. So we could put it like absolute value 10, that would mean magnitude. If we said the magnitude of V, then that would be this right here, right? So we can follow 10 is the length, 53.3, follow 53.3 up. There's 10 is the length. If you wanted to sketch some of these numbers, that'd be good practice for you. Hopefully your professor even quizzes you on it because you're going to need to get pretty used to converting these. Now, you can convert these by hand, and that's an acceptable method. But if you have a TI 36 Pro, it's even faster. We can review these equations. I mean, it's really just basic trigonometry. Back to Chief Sokotoa, that's how you learned it. It still holds true, and that's what we're doing. I find it faster to just go from polar to rectangular to rectangular, or rectangular to polar is the fastest way to do it. On the calculator, if I hit any number, on this TI-36, I hit second complex. Second complex is right above the pi, so if you hit the pi symbol, second pi. And there's different steps, 4 and 5 take me to polar, and step 5 takes me to rectangular. You can also set up your calculator settings to put it in polar or rectangular every time, and you need to get comfortable going back and forth because we'll use it a lot. So if I was looking at converting, here we have the 5 angle 60. If I wanted to sketch that, here's 60, and there's 5 of it is its length. There's angle 60. If I do it on my calculator, the way I would type it is I do 5. You can find the angle under the same thing, second complex, and it gives you the angle. And if I plug it into my calculator, I get 2.5 plus 4.33J. The other way that you could solve for these is that we could take the C, that 5 cosine of 60, 5 cosine of 60 would give me that number, and 5 sine of 60 would give me 4.33. But like I said, shortcuts are better. There's also on the online calculator and on the smartphone calculator, depending on what you're using, there's always a shortcut to go from polar to rectangular and rectangular to polar. So I recommend you get familiar with that and type in them in. So 6 plus 7. And remember on your calculator, if you're typing 6 plus 7J, it's going to be the I. On this calculator, the TI-36, I hit the pi 3 times and it gives me the I. So 6 plus 7I, I go to complex and I want to convert it into polar. 9 9.2, that's a 9, 9.22 angle 49.4 degrees. I recommend doing some of these yourselves and checking these answers to make sure you got it. Here's some properties of J. Like I said, we actually won't be using these at all. But if you were an electrical engineer, then the complex numbers get even more complex. All right, shortcuts for adding and subtracting. In your calculator, it can always handle. The calculator can always do polar and rectangular at the same time. You do not need to convert from polar into rectangular in order to add two rectangular numbers. This is more just how vector math works. And if I think about vectors, right, and I have 6 plus 12j, here's 6 plus 12, 6, 12 is a little bit higher, there's a vector. Well, the way that we put the vectors is we put the tail of one onto the tip of the other, and so 7 plus 2j. So 7 goes out this direction, plus 2. So there's two vectors, and if I wanted to add these, then I put the tail of this one on top. There's the 7 plus 2j that I've taken, and it goes on top. And now it goes right here, and in green, I'll put a new vector. So what is this new vector? This new vector is 13 plus j14. That's how the vector addition works. And we just add the rectangular components. So if you're going to do it by hand, and sometimes it is faster, if you're going to add and subtract complex numbers, then we put it in the rectangular form. Whereas if you're going to multiply it, and I won't draw this out, let's just trust that this is how the multiplication works, is that it's best if we put it into the polar form. If you're going to multiply and divide in the complex numbers, put it into polar form. And what we do here is I take the magnitude, actually I'll put that in green. We'll take the magnitude, and those get multiplied together to give me 12. Whereas if I am doing the angles, I take the angle, and when I'm multiplying, they get added. 70 plus 30 is 100. So we add the angles, the phase angles. Whereas for the magnitudes, we multiply magnitude. Similarly, when we divide the magnitude, but we subtract the angles. Right? We can see that right here. 6 divided by 2, 70 minus 30. So if we're going to do it in multiplying, and we're going to do it where we do it by hand, which sometimes is faster if you're doing especially 2 angle 30 times 1 angle 10. That's faster to maybe just do it by hand than typing all those complex numbers into your calculator. All right, last point is called the reciprocal, which we hardly ever use, but this idea of the complex conjugate we will use a lot. And it is denoted with an asterisk on the equation sheet. Here's an example of where you might see this. Actually, here's one right here. We'll get to this later, but here's max power transfer. Do you see the asterisk right here? There's an asterisk. Also over here, S equals VI, complex conjugate. Right there. There is a shortcut on your calculator under that same complex menu to do complex conjugate, but this one you can do in your head every single time. Because whenever you're doing the complex conjugate, it just means it's reflected upon the x-axis or reflected on real axis, right? So if I'm looking right here, if I had a positive theta angle, well, the conjugate has a negative theta angle. Positive theta angle, negative theta angle. Or if I had a positive A component, that positive A component in the rectangular stays the same, but my positive B now becomes a negative B. It's reflected on the real axis. It's denoted with an asterisk or a little star up by it. So my cheesy joke is that you all go to the complex conjugate of the Naval Academy. That's not funny. All right. These are probably good to do in your calculator. I'll give you the answers right now just so that you could check them later. But this should be converting it to the rectangular, or sorry, the first one. We're going to put it in polar and rectangular. All right, here's the polar, here's the rectangular. All right, 10.61, angle 16.12 degrees. Convert it, 10.19 plus 2.95J. Like I said, do these in your calculator. I'm just giving you these answers to make sure that you're comfortable with it. And if you're not, do it again until you become comfortable with it. So plug this in, you should get 7.33, angle 17 degrees. And converting it to rectangular should give you, that's 7.33K. 7011 plus 2148J. All right, a few more. You can work these on your own and check it with your instructor. It's worth the practice for you. Because now what I want to talk about is the phasor and turning these sinusoidal equations into phasor values. And so whenever it says as a phasor, here's the steps that I said earlier: determine the V peak and the phase angle, the amplitude and the phase. We can take the RMS, and this should say find the RMS phasor. So we can turn these sinusoidal equations into a phasor. Note these old notes have sine. In our new book and the homework problems, it's all cosine. But if we just take it straight from that angle, we won't put everything in this new class back into cosine. For now, we'll just work it with sine because it really, once you're operating in the same sinusoid, it won't matter anymore. All right. So RMS value, we have V peak is equal to 100. So if I wanted the RMS value, the RMS equals to 100 divided by root 2, which is also like multiplying by 0.707. So a lot of students will just use that. So that's 70.7. It has no angle, right? If it had an angle, it would give us one, but it doesn't. So it's 70.7 angle 0. This one does have an angle, and it's positive 45, and there's its V peak. V peak, I'll divide it by root 2, and that gives me 35.35. So if I'm writing this as a phasor, I would write an RMS phasor, 35.35 angle positive 45 degrees. Phase difference, we've kind of already talked about this, is that there could be a leading and a lagging, but how does that look on a phasor graph? And so let's zoom in where we can see this a little bit better, right? So V right here, theta V, reset, theta V in this case is equal to 0. Theta I, we'll just make up a number for it, but theta I is leading, so say it's positive 30 degrees, right? So how does that look on a phasor plot? Well, V is along the 0, right? There's V, and where's I? I is positive 30. So you could determine the phase difference between two time domain and also see that in the phasor domain. There's the theta of I is equal to 30. If one wasn't 0, say that you just wanted to plot it on another x-axis, if you had a theta V equal to 10 and a theta I equal to negative 45, right? Theta V would be 10, negative I 45, and we could analyze and see that there's 55 degrees difference between them. Zoom back out. Here's where we talk about the trigonometry equations, which is that right here. In fact, I'm going to box it and I'm going to highlight it. So for the rest of our class, a lot of the examples may be given in sine, but in the homeworks, it will be given in cosine. And if you need to put it back into cosine, then we just, the sine equation, we add 90 to the phase angle. That's it. See right here. To go from sine to cosine, we add 90. To go from cosine to sine, we subtract 90. How does that look on a circuit? Is that it does have a sinusoidal equation. That's why this little AC source has a little sine wave inside of it. And it is changing as a function of time. But once we plug it into the circuit, we're pretty much going to use our phasor value whenever we plug these in. And that's because the phasor domain is what allows us to easily solve it with all the circuit components later. And with that, I'll conclude 14A.